Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Antarctica stretches across 14 million square kilometers at the bottom of our planet, holding secrets that could reshape civilization as we know it. This frozen continent contains 90% of Earth's fresh water, locked away in ice sheets that have persisted for millions of years. To understand the true magnitude of Antarctica's frozen treasure, imagine every lake, river, and reservoir on Earth combined. Then multiply that volume by 60. That's the scale of water imprisoned in Antarctic ice. The Antarctic ice sheet isn't uniform. Scientists divide it into two distinct regions: the larger East Antarctic ice sheet, which sits primarily on land above sea level, and the smaller but equally important West Antarctic ice sheet, much of which rests on bedrock below sea level. These ice masses average over 2 kilometers thick, with some areas reaching depths of nearly 5 kilometers. The Ross Ice Shelf alone, floating on the ocean's surface, spans an area larger than California. But what if this entire frozen empire suddenly disappeared? Not gradually over centuries, as climate models predict, but instantaneously, every ice crystal simultaneously transforming into liquid water. This scenario defies natural physics, yet exploring its consequences reveals the hidden connections between Antarctica and global systems that sustain human civilization. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The immediate transformation would release approximately 26.5 million cubic kilometers of water into the world's oceans. To visualize this volume, picture a sphere of pure water with a radius of 184 kilometers, nearly the distance from New York to Philadelphia. This water mass, suddenly liberated from its frozen state, would begin an unstoppable journey across the planet's surface. The physics of this release involves more than simple melting. Antarctica's ice exerts tremendous pressure on the underlying bedrock through its sheer weight. Geologists have discovered that removing this ice load would trigger immediate geological responses. The land beneath would begin rising, a process called post-glacial rebound, but this adjustment would take millennia to complete. Initially, vast areas of newly exposed bedrock would sit below sea level, creating temporary inland seas. The energy required for such instantaneous melting staggers the imagination. Transforming ice into water requires 334,000 joules per kilogram, enough energy to power an average American home for 3 days just to melt 1 cubic meter of ice. Multiplying this across Antarctica's entire ice mass reveals energy requirements equivalent to humanity's total power consumption for over 2,000 years. Ocean currents would immediately begin redistributing this massive water influx. The Southern Ocean, which encircles Antarctica, would become the epicenter of unprecedented hydrological chaos. Cold, fresh water would interact violently with warmer, saltier marine environments, disrupting thermohaline circulation patterns that have remained stable for millennia. The gravitational effects alone would reshape our planet. Antarctica's ice mass is so enormous that it actually warps Earth's gravitational field in its vicinity. Removing this mass would cause measurable changes in gravity across the southern hemisphere, affecting everything from satellite orbits to sensitive scientific instruments. Regional atmospheric conditions would transform instantly. Antarctica currently reflects over 80% of incoming solar radiation back to space through its white surface, a phenomenon scientists call the albedo effect. Replacing this reflective ice with dark ocean water or exposed rock would fundamentally alter regional heat absorption, creating immediate temperature gradients that would drive powerful new weather systems across the southern hemisphere. The moment Antarctica's ice transforms into liquid water, Earth's oceans would rise by approximately 58.3 meters, nearly 200 feet. This isn't merely a number on a climate scientist's chart. It represents the complete submersion of coastal civilizations across every continent. To understand this transformation's magnitude, Consider that this rise would place the Statue of Liberty underwater, up to her torch, leave only the upper floors of most skyscrapers visible in Manhattan, and transform geography textbooks into archaeological curiosities. The water wouldn't distribute evenly across Earth's surface. Ocean dynamics, gravitational effects, and rotation create complex patterns that oceanographers call geoid variations. These variations mean some regions would experience sea level rise exceeding 70 meters, while others might see increases of only 40 meters. The Indian Ocean would bear the heaviest burden, receiving disproportionate volumes due to its proximity to Antarctica and existing current patterns. Coastal megacities would vanish beneath the waves within hours. London, New York, Tokyo, Mumbai, Shanghai, and countless other urban centers house over 600 million people whose lives depend on current sea levels. The Thames Barrier, designed to protect London from storm surges of a few meters, would prove utterly insignificant against a 58-meter rise. Similarly, the Netherlands' elaborate system of dikes and seawalls, engineering marvels that protect millions from existing sea levels, would become submerged monuments to human ingenuity rendered obsolete by Antarctic ice melt. The flooding wouldn't stop at coastlines. River deltas, those fertile regions where major rivers meet the sea, would experience catastrophic backflow as ocean water forced its way inland. The Mississippi Delta would see saltwater penetration extending hundreds of kilometers upstream. The Nile Delta, humanity's agricultural foundation for 5,000 years, would transform into a vast saltwater bay extending to Cairo. The Ganges-Brahmaputra Delta, supporting over 100 million people, would become an inland sea, ocean. Basin geometry would fundamentally change. The Atlantic's profile would shift dramatically, with new coastlines carved deep into continental interiors. The Mediterranean Sea would expand beyond recognition, flooding the Po Valley in Italy and creating new waterways where ancient civilizations once flourished. The Black Sea would connect directly with the Caspian through flooded lowlands, creating unprecedented inland water networks. Continental shelves, those underwater extensions of land masses that support crucial marine ecosystems, would find themselves at depths previously occupied by abyssal plains. Fishing grounds that have sustained human populations for millennia would relocate to entirely new regions, assuming marine life could adapt to such rapid environmental changes. The Grand Banks off Newfoundland, historically among Earth's richest fishing areas, would shift hundreds of kilometers inland from their current positions. Island nations would simply cease to exist. The Maldives, Marshall Islands, Tuvalu, and dozens of other low-lying countries would disappear completely beneath the waves. Even larger islands would transform beyond recognition. Madagascar would lose its coastal plains, becoming a narrow, mountainous ridge surrounded by deep water. The Florida Keys would vanish entirely, while the Florida Peninsula would shrink to a small island centered around its highest elevations. The sheer volume of water movement would generate massive global currents unlike anything in Earth's recent geological history. These currents would carry unprecedented amounts of sediment, debris, and displaced materials across ocean basins. Underwater landslides triggered by rapid water loading would reshape seafloor topography, potentially generating tsunamis that would compound the catastrophic flooding from the initial sea level rise. Atmospheric moisture content would increase dramatically as vast new ocean surfaces began evaporating water into the atmosphere. This increased evaporation would fundamentally alter global precipitation patterns, creating feedback loops that would accelerate climate changes already set in motion by the loss of Antarctica's reflective ice surface. The instant loss of Antarctica's ice would trigger atmospheric chaos beyond anything recorded in human history. Our planet's weather systems depend on delicate temperature gradients and pressure differentials that Antarctica's ice sheet has helped maintain for millions of years. With this stabilizing influence suddenly removed, global atmospheric circulation would enter a period of violent reorganization that would make the most severe storms in recorded history seem gentle by comparison. The key jet streams, those high-altitude rivers of air that guide weather patterns across continents, would destabilize immediately. Currently, The temperature difference between Antarctica's frigid surface and warmer regions to the north helps maintain these crucial atmospheric highways. Without this temperature anchor, jet streams would begin meandering wildly, carrying tropical heat toward polar regions and Arctic cold toward the equator in unprecedented patterns. Weather forecasting would become virtually impossible as atmospheric models struggle to predict patterns without historical precedent. Ocean circulation would collapse within months. The thermohaline circulation, often called the global conveyor belt, depends on cold, dense water, sinking near polar regions and warmer water rising in tropical areas. This circulation system transports heat around the globe and drives regional climate patterns that billions of people depend upon. The massive influx of cold, fresh water from melted Antarctic ice would disrupt the salinity gradients that power this system, potentially stopping circulation entirely in some ocean basins. The Gulf Stream, which keeps Western Europe habitable despite its northern latitude, would weaken dramatically or cease entirely. London sits at the same latitude as Labrador, Canada, but enjoys a temperate climate because the Gulf Stream carries warm Caribbean water northward. Without this heat transport, Western Europe would experience temperature drops of 10 to 15 degrees Celsius within years, transforming agricultural regions into frozen wastelands unsuitable for current farming practices. Monsoon patterns across Asia and Africa would collapse or reverse. Over 3 billion people depend on monsoons for agricultural water supplies, from India's rice paddies to the Sahel's marginal farmlands. These seasonal wind patterns develop from temperature differences between land and ocean surfaces. The massive changes in ocean temperature distribution would fundamentally alter these gradients, potentially bringing unprecedented droughts to regions that depend on seasonal rains or delivering torrential precipitation to areas unprepared for such. Volumes, hurricane and typhoon formation would enter uncharted territory. These storms draw energy from warm ocean surfaces, and the redistribution of ocean temperatures would create new zones of storm formation while eliminating others. Traditional hurricane seasons would become meaningless as storms could develop year-round in new regions. Coastal areas that have never experienced hurricanes might face multiple major storms annually, while traditional hurricane zones might become relatively calm. The loss of Antarctica's albedo effect would accelerate global warming beyond current climate projections. Ice reflects approximately 90% of incoming solar radiation, while dark ocean water absorbs over 90%. Replacing Antarctica's reflective surface with heat-absorbing water would add warming equivalent to doubling atmospheric carbon dioxide concentrations. This feedback loop would drive atmospheric temperatures higher, increasing evaporation rates and water vapor content, which would trap additional heat in a runaway warming scenario. Regional precipitation patterns would shift chaotically. The Amazon rainforest relies on atmospheric moisture recycling, where evaporation from the Atlantic Ocean falls as rain, which then evaporates again to provide moisture for inland regions. Disrupted ocean currents would alter this moisture supply, potentially transforming the world's largest rainforest into savanna or desert. Similarly, the Sahara Desert's extent depends partly on atmospheric circulation patterns that would change dramatically, possibly bringing precipitation to regions that haven't seen significant rainfall in millennia. Mountain weather systems would transform as global circulation patterns shifted. The Himalayas, Andes, and other major mountain ranges create their own weather through orographic lifting, where air masses forced upward by mountain slopes cool and release moisture. Changes in prevailing wind directions and atmospheric moisture content would alter precipitation patterns on these mountains, affecting river systems that billions of people depend upon for fresh water. The polar vortex, that mass of cold air, normally confined to polar regions, would destabilize completely. Without Antarctica's extreme cold to anchor it, this system would break apart, sending frigid air masses wandering across lower latitudes while allowing warm air to penetrate regions typically protected by polar circulation. Temperature swings of 30 to 40 degrees Celsius could occur within days as these destabilized air masses collided. The ecological aftermath of Antarctica's instantaneous ice loss would trigger the most severe mass extinction event since the asteroid impact that eliminated the dinosaurs 66 million years ago. The speed of this transformation would prevent evolutionary adaptation, creating a cascade of ecosystem collapses that would fundamentally reshape life on Earth within decades rather than the millennia typically required for such dramatic biological reorganization. Marine ecosystems would face immediate catastrophic disruption. The sudden influx of cold fresh water would alter ocean chemistry across all basins, changing salinity levels that marine organisms have adapted to over millions of years. Phytoplankton, the microscopic organisms that form the foundation of oceanic food webs and produce over 50% of Earth's oxygen, cannot tolerate rapid salinity changes. Mass die-offs of these crucial organisms would begin within weeks, eliminating the primary food source for countless marine species while simultaneously reducing global oxygen production. Coral reefs, already stressed by current climate changes, would experience complete ecosystem collapse. The temperature and chemistry changes accompanying massive sea level rise would exceed all tolerance thresholds for reef-building corals. The Great Barrier Reef, Mesoamerican Reef, and Caribbean Reef systems would experience total bleaching events within months. These vibrant underwater cities, which support 25% of all marine species, despite occupying less than 1% of ocean area, would transform into lifeless calcium carbonate graveyards. Coastal wetlands, among Earth's most productive ecosystems, would vanish beneath rising seas. Salt marshes, mangrove forests, and estuaries serve as nurseries for countless marine species and breeding grounds for migratory birds. The Everglades, Sundarbans, and similar wetland complexes would disappear entirely, eliminating crucial habitat for species ranging from manatees to tigers. Over 40% of all animal species depend on wetlands at some point in their life cycles, making these habitat losses particularly devastating. Arctic and Antarctic ecosystems would face complete transformation. Polar bears, penguins, seals, and countless other species adapted to ice-dependent lifestyles would find their world fundamentally altered overnight. Emperor penguins, which require stable sea ice for breeding, would lose all traditional nesting sites. Arctic foxes, polar bears, and ringed seals would face immediate habitat elimination, with no time for behavioral or evolutionary adaptation to ice-free environments. Terrestrial ecosystems would struggle with unprecedented climate disruption. The chaotic weather patterns and temperature swings would stress plant communities beyond their adaptive capacity. Forests that have developed over centuries or millennia would face temperature extremes, precipitation changes, and storm intensities that exceed their tolerance ranges. The Amazon rainforest, often called Earth's lungs for its oxygen production and carbon storage, would likely transition to grassland or desert as precipitation patterns shifted away from supporting dense forest growth. Mountain ecosystems would experience particularly severe impacts. Alpine species, adapted to specific elevation zones with distinct temperature and precipitation regimes, would find their habitat zones shifting faster than they could migrate. Many mountain species, already restricted to narrow elevation bands, would face extinction as suitable habitat disappeared entirely. The cloud forests of Central America, home to countless endemic species, would lose the specific climate conditions that create their persistent cloud cover. Agricultural systems supporting human civilization would collapse in most regions. But the sea, crops that feed 8 billion people developed under relatively stable climate conditions that would no longer exist. Wheat, rice, maize, and other staple grains require specific temperature and precipitation patterns during critical growth periods. The chaotic weather patterns and shifted seasonal cycles would make traditional agriculture impossible across vast regions, creating global food security crises that would compound other humanitarian disasters. Freshwater ecosystems would face contamination from saltwater intrusion, extending far inland along river systems. Many freshwater fish species cannot tolerate saltwater and would die as coastal flooding carried saltwater hundreds of kilometers upstream. Lake ecosystems near new coastlines would transform from freshwater to brackish or saltwater environments, eliminating endemic species that evolved in isolation over millions of years. Migratory species would face particular challenges as their navigation systems and stopping points disappeared. Birds that migrate thousands of kilometers, using coastal landmarks and stopover sites, would find their routes devastated. Sea turtles, which use magnetic fields and coastal features for navigation, would struggle to locate nesting beaches that no longer exist. Whale migration patterns developed over millions of years would become obsolete as ocean circulation patterns shifted dramatically. The pollination networks that support terrestrial plant reproduction would fragment severely. Many plants depend on specific pollinator species that are adapted to particular climate conditions and flowering schedules. The disrupted seasonal patterns and habitat losses would break these relationships, leading to cascading effects throughout plant communities and the animals that depend on them for food and shelter. Human civilization, built over 10 millennia around current coastlines and climate patterns, would face immediate collapse across most inhabited regions. 8 billion people would confront displacement scenarios beyond any historical precedent, creating refugee crises that would overwhelm every existing international support system. The infrastructure supporting modern life would prove utterly inadequate for the new reality of a world transformed overnight by risen seas and chaotic weather. Cities housing over half of humanity would become uninhabitable within hours. New York's subway system would flood completely, transforming into underwater tunnels that could never be reclaimed. London's underground would become a vast network of submerged caves. Tokyo's elaborate infrastructure, from railways to power grids, would short-circuit as saltwater penetrated electrical systems never designed for marine environments. The collective economic value of infrastructure lost to flooding would exceed the entire global economy's annual output by orders of magnitude. Agricultural collapse would trigger global famine within months. The world's major grain-producing regions, the American Midwest, Ukrainian steppes, Argentine pampas, would face either direct flooding or climate disruption that would eliminate crop production. The just-in-time global food distribution system, designed around predictable transportation networks and seasonal production cycles, would shatter as ports flooded and weather patterns made transportation impossible. Food reserves, typically sufficient for only a few months in most countries, would prove catastrophically inadequate. Freshwater supplies would face contamination across vast regions as saltwater intrusion poisoned groundwater aquifers that took millennia to fill. The Ogallala Aquifer, which provides irrigation water for much of American agriculture, would become contaminated with saltwater penetrating from newly formed inland seas. River systems worldwide would carry saltwater far upstream, rendering traditional water treatment plants useless. Desalination technology, while theoretically capable of addressing some needs, requires enormous energy inputs and infrastructure that would be unavailable during the chaos following such catastrophic changes. Energy infrastructure would fail catastrophically as power generation facilities flooded and distribution networks collapsed. Nuclear power plants, many located near coastlines for cooling water access, would face emergency shutdowns as saltwater flooded control systems. Coal and natural gas plants would lose fuel supply chains as transportation networks collapsed. Renewable energy installations would prove inadequate to replace lost capacity, while simultaneously supporting the massive energy requirements for desalination and refugee resettlement. Military forces worldwide would shift from national defense to disaster response, but would prove inadequate for the scale of required intervention. The logistics of evacuating hundreds of millions of people from flooded coastal areas would exceed all existing military transportation capacity. Naval assets designed for current sea levels would struggle to navigate newly formed inland seas, while avoiding submerged obstacles like skyscrapers and bridges. Air forces would face overwhelming demand for transport and supply missions that would exhaust fuel reserves and maintenance capabilities within weeks. Governments would lose effective control as communication networks failed and administrative centers flooded. Democracy would prove impossible when populations face immediate survival needs and traditional voting districts lie underwater. International borders would become meaningless as millions of climate refugees moved inland seeking habitable territory. The Westphalian system of nation-states, developed over centuries around fixed territorial boundaries, would prove obsolete when those boundaries disappeared beneath rising seas. Economic systems would cease functioning as traditional concepts. Of property ownership became meaningless. Real estate markets would collapse completely when most valuable properties lay underwater. Insurance companies would declare bankruptcy simultaneously as claims exceeded all possible payouts by thousands of times. Banking systems would fail as loans secured by flooded properties became worthless while borrowers dispersed as refugees. Currency systems would face hyperinflation or collapse as governments lost tax bases and printed money to fund emergency responses. Supply chains supporting global trade would disappear as major ports flooded permanently. The container shipping system that moves 90% of global trade relies on specific port facilities and predictable transportation networks that would vanish overnight. Manufacturing centers worldwide would lose both suppliers and customers as economic networks. Fragmented beyond repair, the complex interdependencies of modern production, where components cross multiple borders before final assembly, would prove impossible to maintain. Social structures would fragment under unprecedented stress as communities scattered and traditional support networks disappeared. Families would face separation as transportation networks collapsed and communication systems failed. Religious and cultural institutions would struggle to maintain cohesion when their physical centers flooded and congregations dispersed globally. Educational systems would cease functioning as schools flooded and teachers joined refugee populations seeking basic survival. Healthcare systems, already strained by normal demands, would face overwhelming patient loads from drowning, injuries, and disease outbreaks while losing most hospital facilities to flooding. Medical supply chains would collapse with other distribution networks. Sanitation systems would fail completely in flooded areas, creating ideal conditions for epidemic diseases. Mental health support, crucial during such traumatic transitions, would be unavailable as healthcare professionals focused on immediate physical survival needs. The technological civilization that defines modern human life would prove surprisingly fragile when foundational assumptions about geography and climate suddenly changed. Server farms and internet infrastructure, concentrated in coastal areas for cost and connectivity advantages, would flood permanently. Satellite networks would lose ground control stations and maintenance facilities. The global positioning systems that modern navigation depends upon would lose reference points as landmarks disappeared underwater. The geological consequences of instantaneous ice loss would trigger planetary adjustments, not seen since the last ice age, fundamentally reshaping Earth's crustal structure and triggering seismic events that would compound the catastrophic flooding and climate disruption. The sheer weight of Antarctica's ice, approximately 24 trillion tons, has pressed down on the continent's bedrock for millions of years, creating a depression that would begin rebounding immediately upon ice removal. Post-glacial rebound would commence instantly, but unfold over millennia. The Antarctic landmass would begin rising at rates potentially exceeding several centimeters per year, creating unprecedented geological instability. This rapid vertical movement would generate massive earthquakes as bedrock adjusted to reduced pressure. Seismic events exceeding magnitude 9.0 would become common across Antarctica and surrounding regions as crustal blocks shifted to establish new equilibrium positions. The redistribution of water mass across Earth's surface would alter the planet's rotational characteristics, adding 26.5 million cubic kilometers of water to ocean basins would change Earth's moment of inertia, potentially affecting rotation speed and axis orientation. While these changes would be small, they would be measurable by precise scientific instruments and could influence everything from satellite orbits to the length of days over geological timescales. Volcanic activity would increase dramatically. In regions experiencing rapid pressure changes, the removal of ice weight would reduce pressure on underlying magma chambers, potentially triggering eruptions in volcanic systems that have remained dormant for millennia. Iceland, situated between active tectonic plates and currently suppressed by glacial weight, would likely experience unprecedented volcanic activity as pressure release allowed magma to reach the surface more easily. Submarine earthquakes and landslides would become frequent as ocean floors adjusted to increased water pressure from higher sea levels. Continental shelves loaded with additional water weight would experience massive slope failures as sediments destabilized. These underwater landslides could generate tsunamis that would add to the catastrophic flooding from initial sea level rise, creating secondary waves that could reach hundreds of meters above normal sea levels in coastal regions. The gravitational redistribution would affect tidal patterns globally. Ocean tides result from gravitational interactions between Earth, Moon, and Sun, but they also depend on Earth's mass distribution. Moving massive amounts of water from Antarctic ice to ocean basins would alter local gravitational fields sufficiently to change tidal amplitudes and timing. Some coastal regions might experience higher high tides and lower low tides, while others could see reduced tidal ranges that would affect coastal ecosystems and navigation. Atmospheric pressure patterns would shift as the planet's mass distribution changed. The water vapor content increase from expanded ocean surfaces would alter atmospheric density patterns. Weather systems derive energy from pressure gradients, and changes in global pressure distribution could affect storm formation and movement patterns beyond those caused by temperature and circulation changes. Mountain ranges worldwide would experience increased seismic activity as global stress patterns shifted. The Himalayas, Andes, Alps, and other major mountain chains would face altered tectonic pressures as Earth's crust adjusted to new mass distributions. This could accelerate mountain building processes in some regions while increasing erosion and instability in others. The Pacific Ring of Fire, already seismically active, would likely experience enhanced volcanic and earthquake activity. Magnetic field variations could occur as core mantle boundary conditions changed. Earth's magnetic field results from fluid motions in the planet's outer core, and significant changes in crustal loading could potentially influence these deep Earth processes. While major magnetic field reversals typically occur over thousands of years, rapid surface changes might trigger measurable variations in magnetic field strength and orientation. Permafrost regions would destabilize rapidly as altered atmospheric circulation brought different temperature regimes to polar areas. The permafrost that currently locks vast amounts of carbon and methane would begin thawing at accelerated rates, releasing greenhouse gases that would further accelerate climate changes. This represents a massive positive feedback loop where ice loss leads to permafrost thaw, which leads to additional warming, which leads to more ice loss in remaining glaciated regions. Groundwater systems would experience fundamental reorganization as new pressure gradients developed. Aquifer systems that developed over millions of years under current conditions would face altered recharge and discharge patterns. Some aquifers might drain rapidly toward newly formed inland seas, while others could experience increased pressure from overlying water masses. Groundwater contamination would spread rapidly as saltwater intrusion affected continental-scale water resources. Cave systems and underground networks would flood as water tables rose dramatically in many regions. Limestone cave systems, which often extend far below current water tables, would become completely submerged. These changes would affect underground ecosystems and eliminate speleological features that took millions of years to develop. Underground rivers and drainage systems would reverse direction or become part of larger underground lake systems. The landscape transformation would proceed at rates that exceed normal geological processes by orders of magnitude. Erosion patterns would intensify dramatically as increased precipitation and storm activity carved new drainage patterns. River channels would adjust to new base levels as ocean waters extended far inland. Coastal erosion would accelerate as wave action attacked newly submerged terrain that had never experienced marine conditions. The recovery timeline from complete Antarctic ice loss would stretch across geological epochs, fundamentally altering evolution's trajectory and creating an Earth system unlike anything in the planet's 4.6 billion-year history. Understanding this deep future requires examining how biological systems, climate patterns, and planetary processes would eventually establish new equilibrium states after the initial catastrophic adjustments stabilized over thousands of years. Ecosystem recovery would follow entirely new evolutionary pathways as surviving species adapted to transformed environments. The mass extinction event accompanying ice loss would eliminate perhaps 70 to 80% of existing species, creating ecological niches that would drive rapid evolutionary radiation among survivors. Marine ecosystems would likely recover first, as ocean environments tend to be more stable than terrestrial ones once new circulation patterns established themselves after several centuries of adjustment. New ocean circulation patterns would eventually stabilize, but they would differ fundamentally from current systems. The thermohaline circulation would restart once temperature and salinity gradients re-established themselves, but the driving forces would be distributed differently across ocean basins. Arctic regions, no longer constrained by permanent ice cover, would become major heat sinks drawing warm water northward through new current pathways. These altered circulation patterns would support different marine ecosystems than those that exist today. Climate stabilization would occur over millennial timescales as new feedback loops developed. The loss of ice albedo would represent a permanent change to Earth's energy balance, leading to a stable climate state several degrees warmer than current conditions. This warmer world would support different vegetation patterns, with forests potentially extending to polar regions and tropical conditions expanding toward current temperate zones. The new climate equilibrium would resemble Earth's condition during the Eocene epoch, approximately 50 million years ago. Continental rebound would continue for tens of thousands of years as Antarctic bedrock slowly rose toward isostatic equilibrium. This process would gradually expose new land areas while continuing to generate seismic activity, though at decreasing intensity over time. Some regions of Antarctica might eventually rise above sea level, creating new land masses that would be colonized by organisms dispersing from other continents. These emerging lands would support entirely new ecosystems as plants and animals adapted to previously unknown environments. Atmospheric composition would evolve as new vegetation patterns altered carbon cycling. The expanded ocean surface area would initially increase atmospheric moisture content, but new precipitation patterns would eventually support larger terrestrial biomass in some regions. Tropical forests might expand significantly, potentially offsetting some carbon dioxide increases through enhanced photosynthesis. However, the permanent loss of ice-stored carbon and altered permafrost dynamics would maintain atmospheric carbon dioxide at levels significantly higher than current concentrations. Species migration and evolution would accelerate in response to new environmental pressures and opportunities. Organisms surviving the initial extinction event would face reduced competition and abundant new niches, driving rapid adaptive radiation. Island biogeography principles suggest that surviving populations would diversify quickly to fill empty ecological roles. Marine organisms might evolve rapidly to exploit new deep-water environments created by higher sea levels, while terrestrial species would adapt to altered precipitation and temperature regimes. Human civilization, if it survived the initial catastrophe, would require complete reconstruction around new geographical and climatic realities. Population levels would likely remain reduced for centuries as societies rebuilt social structures and developed technologies adapted to the transformed world. Coastal civilizations would be impossible for millennia, requiring human societies to develop around inland water resources and elevated terrain. Agricultural systems would need to be redesigned around new climate patterns and available land areas. Technological development would follow different pathways as societies adapted to resource distributions and environmental conditions unlike those that shaped previous human development. Energy systems would necessarily rely heavily on renewable sources as fossil fuel infrastructure and extraction became impossible in many regions. Water management would become the fundamental technology around which other developments occurred, requiring innovations in desalination, distribution, and conservation that exceed current capabilities. River systems would carve new channels and establish new drainage patterns over thousands of years as landscapes adjusted to altered precipitation patterns and base levels. Some current river systems would become submerged fjords or inland seas, while new drainage networks would develop on exposed continental shelf areas and rebounding Antarctic terrain. These new river systems would support different types of aquatic ecosystems and provide freshwater resources for recovering terrestrial communities. Atmospheric circulation would eventually stabilize into new patterns that would define weather systems for millions of years. The new jet stream positions, monsoon patterns, and cyclone development zones would become the background conditions for all future climate evolution. These new patterns would influence everything from seasonal cycles to long-term climate stability, creating the atmospheric framework within which new ecosystems would develop and persist. The deep future Earth emerging from complete Antarctic ice loss would represent a fundamentally different planet, one where coastlines, climate zones, and biological communities bear little resemblance to current conditions. This transformed world would eventually support rich ecosystems and potentially complex civilizations, but they would develop within environmental parameters that current life forms and human societies could never survive. The experiment of complete ice loss would essentially reset Earth's biological and climatic evolution, creating new trajectories that would unfold across millions of years of planetary development. Understanding these long-term consequences emphasizes how profoundly Antarctica's ice connects to every aspect of our planet's function, from immediate weather patterns to the deep future of evolution itself.